This section is all about the transformation of functions, which hopefully at this point you should be familiar with that term. Basically, we're just going to move, stretch, change the original functions by some addition and subtraction, some multiplication, some scalars there. The first thing I want to talk about is what is a parent function. A parent function is the basic function with the simplest graph within the family of functions. Some of these examples, which you have seen before, are your basic x squared, which would be your quadratic, your absolute value, which would be that V shape, and then your standard linear. And so we've already reviewed those. We've actually already graphed some of those in this section. And so now we're going to move on. So I do want to refer you back to the comprehensive list of parent functions that we're going to look at in this chapter. The first three were just examples, but you do have other functions that you might not be as familiar with. So obviously, all of these you're familiar. The cubic function is one that we're going to start shifting around well as the square and cubic root. You can see how the square root looks similar to this parabola sideways, but of course we have some limitations on negatives. The cubic root looks like that cubic function sideways as well. We do have exponential functions. Later on this year, we will deal with logarithmic functions. And then we have reciprocal functions. So as we get into rationals with that denominator, you'll see, should be familiar with those infinite limits there because of that zero in the denominator. And so these are kind of a more comprehensive list of those parent functions. At translating these functions when they are shifted. And so a translation occurs when the graph is shifted horizontally or vertically. So first, let's talk about a vertical translation. So vertical translation, meaning that we are going to move this function up or down. The standard form of a vertical translation is that f of x, and you can see that it is an addition out here outside of the function itself. What you'll notice is that when it is added outside of the function, that function moves up. When it is subtracted, that function moves down, however many units that it is being added or subtracted. And this would be your parent function, that absolute value, and this would be the translation of that parent function. A horizontal translation then moves it left and right. The standard form here is that fx minus h. I want to point out that this standard form has a minus there. That's really important because what you'll notice is that if your h is positive, technically it looks negative. So here my h is positive. So here my h is positive too because there was already a negative here and it moved to the right. Here, my h is a negative. Minus a negative makes that plus, and it moved to the left. But what I want you to know is that it's the opposite of what you would think. So even though you see a negative here, your original function had a minus, so that means that 2 has to be positive, which technically moves it to the right. This is technically minus a negative 3. So in general form here, this is x minus some number and that number being negative 3. And that's why those are opposite of the way you would think when you first see them. So just to recap, your vertical translations, remember to go up and down, you're outside of the function. To go left and right, you're inside of the function. On the outside, if it's positive, you're going to go up, negative, you're going to go down. Remember, we're talking about the h here, not what you see visually. And so when you see a minus, that means your h is positive, you're going to go right. When you see a plus, that means your h is negative and you're going to go left. So let's look at this particular graph. The first thing you want to do when you go to graph these is you want to recognize your parent function. And so this squared here indicates that we have a parent function that looks like this, which in your mind, when you're sketching, you should think parabola there. On the inside, we have a plus one, which means on the inside, we actually have minus a negative. So we are actually going to go left 1 unit. And then on the outside, we have a minus 2, which means we are going to go down 2 units. So while our standard parabola would put us right here, we're going to shift that. And so we are going to shift that to the right. So that vertex there is going to go to the right. And then we're going to shift it down 1, 2. So our new vertex of this function is actually going to be right here to the left 1, down 2. And then we are going to graph that function right there. And it's sketching, it doesn't have to be perfect. It does talk about the domain and range. And so when we talk about domain, remember we're talking about x values. Well, it actually, even though it looks like it goes infinitely up, it also goes infinitely left and infinitely right, and there are no breaks. So my domain for here would be x would be all real numbers, just all real numbers for that. My range is a little bit different. My range is my y value, and clearly I don't go infinitely down here. I actually have a starting point. My starting point is at -2. And so this is going to be y, anything bigger than -2, and it includes -2. And so it's going to look like that. If we were to do that in, our interval notation, we would just do something like this. Interval notation for my range would just be all numbers there. So now we move to reflections. Reflections just really exactly what it sounds like. We should know this term from geometry. It just flips it across an axis. And so the first one we're going to look at is reflection across the x-axis. And so this is done with negatives. And so you'll see that if you have a negative on the outside of that function, normally the function would be up here and it has just reflected. Think about a mirror. It has gone across that x-axis here. And that's when the negative is in front of the function. You can also have a reflection across the y-axis, which you'll notice for this is that that negative is inside the function. And again, my parent function was here and it just reflected across that y-axis. And so if I'm looking at this particular transformation of this graph, I'm going to first say, what type of graph do I have? Well, the parent function they have given me is x to the fourth. That's not one of your standard ones, but they've given it to you. Well, we can see that two things have happened. First, we can see that that vertex moved. It moved up 3 units. So we know that that x to the fourth is going to go up 3 units. But we can also see that it flipped, and specifically, it reflected across that y-axis. And so if it reflected across the y-axis, then we know that that negative needs to be on the outside of that function. And so we are going to place that negative on the outside of the function so that we know that it has gone across the x-axis, not the y-axis. So the new description for this function is going to be that g of x equals -x to the fourth plus 3. Well, let's look at the second one. So for this one, we have our reciprocal function, which again, they've given you the parent function there. Now remember, these are a little harder to see where what might be happening. Um, First of all, the parent function had this 0 here. And so we can see that it's no longer at 0. And if you have to make a little dashed line to try to figure that out, you can see that it is at 2. So it is shifted left, right. All right. It has also reflected on the x-axis here. And so we're going to need a negative outside of the function. So if we take that original function and we have x, if we were to go inside the function and go right 2, that means it's going to be with that x, not out here. Out here would be an up-down movement, but down here in the denominator with the x would be that left, right. And then a negative outside of that function would look like that. And so we have that g of x. We're saying we have flipped it across the axis and we have shifted it right. Well, just a couple of terms here. Rigid transformation, exactly what it sounds like. Rigid transformations keep the shape of the original graph. Some of these examples would be translations, reflections. Even though the graph may be in a different spot, it still looks the same. And that's what we call a rigid transformation. We also have non-rigid, which exactly again, the way it sounds, that distorts the shape of the graph. These would be if we were to stretch or shrink that graph, then it's going to look different. Could still be on a different spot in the graph. You could have both in the same transformation, but the moving left, right, up, down is not what changed the graph. What changes the graph is if you stretch it or skew it vertically or horizontally. And so if we look at this vertical stretch, you're going to see that we have a coefficient now. We have a scalar that is multiplying it. And so if that number in front of the function, we're not putting it inside the function, but in front of the function is larger than one, and you can see absolute value because remember our negatives just flip it, reflect it. So we're only looking at the absolute value here. If that's greater than one, then it is going to stretch it. And sometimes these are hard to see visually, but basically what it's doing is it's pulling it upwards when you multiply on the outside. And then to shrink it, if that number or that absolute value is less than one, it's going to pull it towards the x graph. So you can see here that this 2 in front of that square root of x is normally right here. This 2 pulled it this direction, where this 1/2 pulled it this direction. You can see it's much closer to the x-axis here, much further away here. And then a horizontal stretch, they look very similar. They don't affect it as much for some of them, depending on the graph, but they actually stretch it towards the x or towards the y-axis here and away from the y-axis. And these actually have it inside the function, inside the function. And so it looks like they lost their square root sign there, but inside the function, that 2 pulled it this direction right here. And inside the function, that 1/2 pulled it this direction. Now, again, they look very similar, but if you remember, that vertical pulled it a lot more because it was pulling it that direction. So depending on your graph, you're going to see these stretches and skews a little bit differently. Again, we're just sketching them, so you're not going to have an exact here, but you do want to recognize which direction it's going to pull it. So think about it like putty. If you were to grab that and pull it one direction, what would that putty look like if you were to pull it? And so as we look at this example here, we can see this is a standard x squared. And again, these sometimes are hard to see, but an x squared is a little bit easier because you can see this one to one, and then it kind of shoots up here a little bit. This is a standard parabola. So you can definitely tell that this is skinnier than that right there. All right. And then, so again, you may not know that it's a factor of that three, but with a x squared, usually you can tell by this first movement. This is a 1, 1 movement, and this is a 1, 3 movement. And that kind of tells you that that's going to be a 3 there. You can also see it's no longer pointing up, it's pointing down. So while the 3 pulled it, right, and stretched it, the negative piece of it flipped it down. And again, we're sketching, but you can see that this graph was stretched vertically, and then it was also reflected. So take a minute and see if you can refer back to your parent function, and see if you can do this particular movement for this one here. Take a minute, see if you can do that, and then come back and we're going to do it together. I like to start by sketching what would be the parent function. And so if you look at your parent function, your cubic function is going to be one that looks kind of like this. This is your cubic function here. And so I always start with the parent function. And then a couple things that I typically do is I'm going to shift left and right first. So this is what I'm going to do first. I am going to probably reflect that second, right? That's inside those parentheses. You can think of parentheses kind of as your order of operations there. Do your parentheses first, right? Then I'm going to stretch that. And then I'm going to move that up and down. And so if I were to shift it first, then it would move my vertex over here. So my vertex would be right there if I were to shift it left too. And then if I were to reflect it across the y-axis, think about reflection, because that's what this one does right here. This reflects it. Reflection is actually going to change the orientation. And so the reflection is going to make it, that vertex is now going to be over on the other side of my y-axis. So my reflection is going to be over here. And think about if I were to reflect this point here over, then all of a sudden this guy is now going this direction, right? We have reflected it, right? And then 1/3 is going to squish that down. So that 1/3 is going to cause this to push down um, horizontally here. And so I am going to have to um, make this wider. So you can only imagine if you were to put pressure on the top and bottom and squish it towards the center, it's going to fatten it up. So it's not actually going to move it, but it is going to potentially fatten that up a little bit. And so you can see that it would probably fatten it some. And then the last thing is we are going to move it down. And so I'm going to take this vertex and I'm going to go down 1, 2, 3, 4, and it's going to be down here. And so my final graph is going to be kind of a fatter cubic function. And hopefully, amidst all of this sketching, you can see my function here. So my function is going to look something like this.